Our project members are Jacob Busekrus, who is presenting Milestone 1 algorithms and their implementation, as well as Algorithm 3, Jimmy Joseph, who is presenting Milestone 2 algorithms and their implementation, and David Edelstein, who is presenting the comparative study results and the conclusion.
Algorithm 1 was implemented by choosing the largest value in the list, or the last index. Since the list is sorted, picking the maximum value and using greedy algorithm to choose the next highest available vault, or vault k units away, will always produce the maximum value. The time complexity of this algorithm is O of n because it'll iterate through every vault. Algorithm 2 was implemented by setting 2 pointers at the start and end of the list. Then, a greedy algorithm was used to pick the greatest value of the 2 pointer values and set the chosen pointer k spots away from its initial position. If it was the end pointer, then it would be positioned k spots to the left, and if it was the beginning pointer, then it would be positioned k spots to the right. This time complexity of this algorithm is also O of n. Milestone 1 implementation. For Milestone 1, we used the Python libraries matplotlib and time to gather and present how the time complexity changed as a function of n and k. Jupyter notebooks were also used as a way to clearly organize code and effectively project plots. This is a demonstration. Algorithm 3 was implemented by recursively checking every possible outcome. For each vault, the algorithm checked if the next possible one would lead to a greater score, and if not, then it would check the next one. This led to a binary decision tree, which in turn has a run complexity of O of 2 to the power of n.
With Algorithm 4, we introduced dynamic programming implementations. There are 2 versions of this algorithm that we have developed. One is 4a, which uses a top-down recursive approach with memoization, and we also have 4b, which instead uses an iterative bottom-up approach. Despite these design differences, they both have a runtime complexity of big theta n plus n minus k squared. This can be derived from the fact that in the relation from I equals k plus 1 to n, there are summations of I minus k, where you run an operation that essentially runs on anything past k. This can be simplified to the relation t equals 1 to n minus k, where the summation is t, and this is a common relation where you can derive the equation n minus k plus 1 over 2. Taking the theta of this, we can simplify this to theta n plus n minus k squared, which is equal to n squared. For algorithm 5, we improve upon algorithm 4a and 4b by leveraging memoization as well as the optimal substructure property. So compared to algorithm 4, where you rely on running an operation of I minus k whenever you have to find the maximum vault number of previously computed vaults, you instead leverage optimal substructure property to recognize that the most recent calculated vault is the optimal solution. Therefore, we can leverage iterative bottom-up dynamic programming to iterate through the array, identify the optimal vault number for each solution, and then reconstruct the index list from the initial iteration. This is a theta of n time complexity, as we are no longer doing the I of k summation operation. Therefore, we can represent this relation as the summation from I1 to n, and it's O of 1. This is directly equal to O of n. And as represented by the chart, we have a linear relationship in program 5. For milestone 2, similar to milestone 1, we use the Python libraries matplotlib, time, and random to generate test data for the algorithm implementations. However, we noticed that during our tests, we encountered Python recursion limits, where Python has a max stack frame of 1,000. Therefore, we customized system variables to manually increase the recursion limits to meet our test results. And this video will demonstrate the program and how we're able to generate graphs. Here we list our size of n's that we're testing. This is a random generation of variables ints from 1 to 100, and here we're manually setting the recursion limit to 1,000,000. Now as I run the Python graph factory, we get the time with the time library and the output. Our graph is generated at the end.
Presented are the runtime graphs for each of our algorithms. Across multiple runs with randomly generated data, all algorithms show highly consistent runtime trends, and Python's built-in timing and sorting functions prove reliable. Our Milestone 1 greedy algorithms 1 and 2 perform as expected, demonstrating the O of n over k plus 1 runtime behavior and scaling almost linearly with input size n. While we could not test large enough inputs to visually confirm the asymptotic convergence to O of n within a feasible runtime, the trends are clear. Algorithm 1 runs faster because it uses a single directional traversal, whereas Algorithm 2 incorporates additional left-right comparisons at each step. This extra logic consistently increases runtime for Algorithm 2. However, Algorithm 2 correctly handles specific unimodal single minimum sequences that Algorithm 1 misses. For Milestone 2, we looked at dynamic programming approaches. Algorithm 3, our naive recursive benchmark, has an exponential runtime growth matching O of 2 to the n, making it impractical even for very small datasets like n equals 50. Algorithm 4a significantly improves efficiency with a roughly quadratic O of n squared behavior using top-down dynamic programming with memorization. The recursion overhead makes it slightly slower than Algorithm 4b. Algorithm 4b uses a bottom-up iterative approach, which avoids that function call overhead and also follows an O of n squared complexity, making it slightly faster in practice. The minor execution time differences between 4a and 4b can also possibly stem from Python-specific list and tuple implementations. Overall, Algorithm 5 performs the best. The algorithm uses optimized dynamic programming and achieves a highly efficient linear O of n runtime, handling large datasets up to n equals 50,000 with negligible delay and producing the optimal solutions. When comparing solution quality between Algorithm 1 and Algorithm 5, we found that while the greedy algorithm usually does not find the optimal solution, its relative correctness gap measured by the error ratio between the optimal and greedy algorithm becomes nearly constant as the number of volts increases past a certain threshold. Through Milestones 1 and 2, we comprehensively explored key algorithmic design paradigms. In Milestone 1, we learned to create, analyze, and test greedy algorithms for the limited volt problems, confirming their linear runtime performance through a comparative study of different selection gaps k across various randomized inputs. This reinforced our understanding of how design choices like traversal direction and data ordering directly influence computational complexity and scalability. Milestone 2 further strengthened this through the implementation of dynamic programming to solve the general volt problem, demonstrating how leveraging optimal substructure and overlapping subproblems can transform exponential searches into efficient polynomial and linear time solutions. The progression from the baseline recursive solution of Algorithm 3 to the memoized 4a algorithm, iterative 4b algorithm, and optimized linear traversal Algorithm 5 bridged the conceptual gap between brute force search and optimized dynamic programming, revealing how problem decomposition and recurrence formulation influence both asymptotic complexity and empirical performance.